Hi grade 11s, we're on to topic 5.5, which is for me the last kind of general type of trig equation you can get. And these are all examples of where you can land up with sine of an angle equals cos of an angle. So this is kind of, the broad thing that I look for when I think it's this type of equation. So there's two different types of examples that can look like this. So let's look at example 1. Example 1 says solve for theta in the following equations, and we kind of touched on this first example in our previous video. Now, the first type of sine equals cos example is where you have sine theta equals cos theta, and you'll notice that they're the same angle. When we get to our second example, we're going to notice that sometimes they're not the same angle, and then we approach it differently. So a couple of things to look out for here. Notice that there's only two terms. There's one term on each side. If I look at question B, which is the same type of equation, there's two terms. So the first important thing is that this specific type of equation only works when there's two terms. One of them has a sine theta and one of them has a cos theta, and they must be the same angle. Okay, so I've written myself a note there that says exactly that. The moment I see a mixture, notice that this is a mixture equation. The moment I see a mixture, I always look for sine squared and cos squared. And can I move away from the idea of being a mixture by using that one identity? Now that's what we did in the previous video. This, however, there's no sine squared, there's no cos squared. And so once I've looked for those, I say to myself, hang on, there's two terms in the equation, and there's sine and cos of the same angle. And when both of these criteria are met, basically this is what I call a tan equation in my head, simply because I know that, like we did in the previous video when we did one of these, I can manipulate this to represent tan. So the moment I see two terms in the equation and sine and cos of the same angle, I know that I can force this to be a tan equation. Okay, now how do I do that? Well, firstly, I always want to get sine theta on the one side and cos theta on the other side. Now in this particular example that was given to me, now what I'm going to do, and I briefly touched on this in the previous video, I'm going to divide by cos theta. Now remember, I've said this before, you're not allowed to divide by a variable, because in any equation, the moment you divide by a variable, you lose a solution. However, I'm not actually dividing by cos here to get rid of it. What happens in this equation is I get a 1 there, so it looks like the cos has disappeared, but you know what, it actually hasn't. All I've done is I've gone and rewritten the cos on the other side of the equation. So there is my cos theta. It's under my sine theta, so it hasn't actually disappeared. However, this is exactly why I call this a tan equation, because the moment you can get sine theta over cos theta in a single term, we know that sine theta over cos theta is tan theta. And so actually this simplifies down to a tan equation. Now if I isolate tan, because this is now basically a very entry-level equation, I get tan theta equals a half. And if I shift tan of a half, I get 26,57 degrees. And if I want to write both solutions, which I always do, I write plus k180, not k360, and that'll automatically generate my second solution. So brief recap. Basically, the moment I see two terms and there's sine and cos of the same angle, I should jump in my head to, oh my word, this is a tan type of equation. I can force this to be tan. So with that in mind, let's look at the next one. So again, if I saw this in a test or exam, I'd say, oh, this is a mixture type of equation. Now don't forget, we want to get rid of the mixture. So the first thing I look for is there a squared, a sine squared or a cos squared? And so I've written myself my note there. In this example, I don't see a sine squared and a cos squared. If I did, I could replace that with 1 minus, cos squared or sine squared. And that means that my equation is no longer a mixture. Now that was topic 5.4. In this one, however, there's no sine squared or cos squared. However, there is a sine theta and a cos theta, and there's two terms, which means I can manipulate this to an example. So for example here, I can manipulate this. If I take over my 2 sine theta, this now becomes the sine theta equals cos theta equation, and it's sine and cos of the same angle, which means that this is a tan example. Because what I'm going to do now is I'm going to divide by cos theta on this side and divide by cos theta on this side. and my left-hand side simplifies down to 3 because my cos's cancel, but my right-hand side has sine theta over cos theta, which is tan theta. So this is 2 tan theta. So this is indeed a tan equation. So this is now an entry level because I'm going to isolate my trig ratio and use shift tan. Now don't forget that tan is allowed to be bigger than 1. Sine and cos are not, but this is 1.5. 3 over 2 is 1.5. Now that's allowed for tan. So when I shift tan of 1.5 or 3 over 2, I don't get an error. I get 56,31 degrees. And don't forget that with tan, we add K180 because that will automatically generate the second solution. So I personally love these type of equations. You have to be able to recognize them, but the more you practice, the easier it is to recognize them. It's a mixture type equation, but it very quickly stops being a mixture. Right, moving on to, you'll notice immediately the difference between example 2 and example 1. Well, first of all, this one doesn't have a sine equals cos, and the angles are not the same. So what does this one look like? Well, let's have a look here. This one says cos theta equals cos 30. So immediately my brain says to me, well, if cos theta equals cos 30, surely theta equals 30 degrees. So I almost want to write that down immediately. Theta could equal 30, simply because cos 30, so cos 30 degrees surely equals cos 30 degrees. So theta could be 30. Now don't forget, the moment you write down a solution, we write plus k 360. K is an element of integers. Now my question is that the only solution? Because don't forget that every single trig equation generally has 2 solutions in the first 360. So this was solution number 1. Is there a second solution? Okay, I want to write on this side, but remember when you first came from the 4 cousins, we learned that there were 4 angles in the first 360 degrees that have the same ratio for sine, cos, and tan. So if we had 30, we know that we can reflect there. So this is actually 150. We know that we can reflect down, so that's actually 180 plus 30, so that's 210. And we know that we could reflect down there, so that's actually kind of like negative 30, or you could think of it as 330. Now that's not my best drawing. But do you remember that there were 4 angles in the first 360 that would all have the same ratio? 2 of them are positive and 2 of them are negative. Now for cos, where was the other positive solution? The other positive the other positive solution was in quadrant 4. So I'm going to say, but hang on, isn't cos of negative 30 degrees, isn't that also the same as cos of 30? And the answer is yes, because don't forget that cos of a negative angle is just the same thing as cos of that angle. So not only does theta possibly equal to 30, but theta could possibly equal to negative 30, simply because cos of negative 30 is actually the same thing as 30. Now we probably should know that because we know that a solution for a cos equation is always plus or minus. And so it makes sense here that yes, theta could be 30, but it could be minus 30. So I've added in my plus k 360 there, and I've just written as myself a note. This is happening because any cos equation has 2 solutions, and we've learned the solutions are always plus or minus. So this was either plus 30 or minus 30, and that's because cos has positive answers in quadrant 1 and 4. Okay, now we want to expand this idea to include sine equals cos type equations, which is what this whole video is about. Now, why is this different to example 1? Is because if you have a look, these angles are different. And the moment the angles are different, there's just no ways that you can get this to be a tan equation. Because tan of an angle is always equal to sine and cos of the same angle. So those angles have to be the same to represent tan. So these angles all have to be the same thing. Now that can't happen here because I have a 3 theta and a theta. So when I see this equation, my first thought is it's a mixture. Okay, so the moment it's a mixture, I don't want it to be a mixture. So I've written down my kind of 3 options there. Firstly, I look for sine squared and cos squared. We've done that. That was topic, the one before this, 5.4. Then I look for what we did in example 1. is there a sine theta equals cos theta? Is it two terms and they're sine and cos of the same angle, in which case I can force that to look like a tan equation. And my third option is when you have sine and cos of not the same angle. And that's what we're working with here. So I've drawn there in my notes, basically sine of a square equals cos of a triangle, so they're not the same angle. And this is what we now need to decide what we're going to do. So it's almost like these are the three different kind of mixtures that you can deal with. So what do we do if they're not the same angles? If I go up to question A, notice how it was very easy to solve an equation if it was cos equals cos, because all we did then was argue that the angles could be equal. So we said, well, theta could equal 30 or negative 30. So it's actually very easy to solve a cos equals cos equation. Similarly, we could solve a sine equals sine equation. So what is my kind of aim here? I want to force this into being a cos equals cos equation. So force this into cos equals cos. Or, and we're going to do both, what about a sine equals sine equation? Now we just solved a cos equals cos, so we know it's possible. So now we have to force it into looking like that so we can solve. The question is, how do we do that? Well, let's first start. So option 1, let's force this into being a cos equals cos equation. Now personally, I like cos equations because I find the plus minus easier than sine. So I would always, if I can, pick option 1. Now how do we do that? Well, if we have a look, cos 3 theta, that's already a cos. So now the question is, can we rewrite sine theta but as cos? So cos of what angle would be the same thing as sine of theta? Now how do you force cos to change its name to sine? You can if you do reduction of 90 degrees. So it's almost like I'm undoing reduction here. If I reduced to sine theta, how could I undo that reduction and write it as a cos? Now, would you agree that 90 minus theta, cos of 90 minus theta, if I was doing reduction, I would say to myself, right, this is in quadrant 1, so cos is positive, which is what I want my answer to be, so this is going to be positive. But I'm working with 90 degrees. So cos of 90 minus theta would reduce down to sine of theta. So it's almost like I'm undoing reduction because I'm trying to force this equation to being a cos equals cos. I'm just going to draw a bubble around this so our working doesn't get confused with our notes. Right, and we've done exactly that now. We've forced this to being a cos equals cos equation. Now I know for a cos equals cos equation, there's two solutions. Either, sorry, I don't know what happened there. Either the angle of 3 theta could be equal to 90 degrees minus theta. So that's option 1. So either they could be equal to each other, or our second solution, and maybe I should leave some space because that's clearly going to need some solving. So, or 3 theta could be equal to the negative version of 90 degrees minus theta. Now let's just think about where that came from. If I go up to question A, that's exactly what I did here. I said either theta could be 30, they could be equal because cos of 30 would equal cos of 30, or theta could be the negative of that angle because cos of negative 30 is the same as cos 30. So a negative version for cos has the same ratio as the positive angle. So that's why I've created two solutions here for cos. Either the two angles are equal to each other, or the one angle is the negative version of the other. Now in both of these examples I then have to add the K360. So I set up both solutions. Remember, don't solve an equation before you've set up both solutions because it leads to mistakes. So I've set up both solutions. So either the angles are equal to each other or it's the negative version. And now basically this becomes a linear equation. So if I just solve this, it's a little bit weird because we've never had an equation with thetas on both sides. But basically I kick over my theta and obviously plus my K360. Now when I divide by 4, remember you divide everything by 4. So I get 22.5 degrees, but this also becomes K90. because don't forget to divide everything. Now, I suppose I don't need that k as element of z every time, so I could have dropped that. Now, in my second solution, this might take a little bit more working because I first have to distribute the 90 degrees. I mean the negative, so it's negative 90 degrees plus theta, plus the usual k360, but now I'm going to minus theta on both sides, so I actually get 2 theta is negative 90. And finally, I get theta is negative 45 degrees, but you divide everything by 2, so this now becomes k 180. And there we go. I forced this, because the angles were different, I forced this into being a cos equals cos. And once it's a cos equals cos, the angles are equal to each other, or once the negative version. Now this, to me, this is the most difficult type of equation because it's a little bit abstract and weird. So we're going to practice quite a few of them. Okay, now the reality that was option 1. I said there's always an option 2. Now I'm going to probably run out of space, but let me kind of box this. So that is option 1. After showing you option 2, I'm probably never going to do option 2 again, simply because I prefer cos equals cos equations, and I'll show you why. However, I think it's important to see both options. So let's just look at option 2, and I'll try and fit it in here. This was not my best effort. So what is option 2? Instead of forcing it into a cos equals cos, can we force it into a sine equals sine? So can we force it into sine of a box equals sine of a triangle? So let's just remember what the question was. The question was cos of 3 theta equals sine of theta. So in this way, can I keep the sine theta, but can I undo reduction on this side? So that would have come from sine, and by the same logic, this would have had to have been 90 minus 3 theta, because that would have been quadrant 1, so it would have been positive, and when I'm working off 90, my name would change to cos. So that would now reduce to sine of 90 minus 3 theta would reduce to cos 3 theta if we were doing reduction. So a sine equation has 2 solutions. So I'm going to do one here, and simply because space is at a premium, I'm going to do my second one there. Now, of course, if you have sine of an angle equals sine of an angle, well, first of all, these angles could be equal. Sine of 30 equals sine of 30. So my first option is that these angles could be exactly the same thing. Oh, that is right, actually. So there we go. Now this just requires solving. So basically, if I bring my theta over, I'll get negative 4 theta, and I'll kick over my 90. And then if I divide by negative 4, guess what I get? 22.5 degrees plus k 90 degrees. Now that's not at all surprising, because if you notice, it's exactly the same answer that I got with cos. Okay, now this is where I feel like the tricky part comes in, the second solution. Now, where is the second solution for sine? Don't forget that the second solution for sine is 180 minus the angle. So when I say on the left-hand side I have 90 degrees minus theta, it could equal theta, as we did in option 1, but it could also equal 180 degrees minus theta. Don't forget that that's the second solution for sine. So I'm following the same pattern. In sine, either the angle is just the angle, or the second solution is 180 minus that angle, and so hence this. Now again, personally, I find this one more difficult. I prefer cos because it's just they're equal to each other, or it's the negative version, and I find that easier. But there's nothing wrong with this version. So now if I skip my negative theta over this side, so I add theta to both sides, I'll get that. And if I minus 90 from both sides, I'll get that. And so once again, if I divide by negative theta, I technically get negative 45. And technically I get minus k, not 360. See how easy it is to make that mistake? Remember, I'm dividing by negative 2, so this is technically k 180. Now it doesn't actually matter that it's negative or positive, because remember, k is an integer. But again, unsurprising, because the answer is exactly the same as what I got with cos. Now I'm sorry, this is a very messy page, but I wanted to show you both because both are completely fine and you must choose what works for you. You also sometimes need to notice that sometimes you won't get answers that are written the same, but if you add the 360, if you add the 180, it gets to what the cos answer was. So they actually always are equivalent answers. Sometimes they just look a little bit different. Now, in the interest of time, I'm going to stick to doing the cos version. and not the sine version, but you can always try the sine version and you'll get the same answer. So let's look at the next one. Question C, cos of theta minus 20 equals sine 2 theta. So let's just quickly talk through the process when you hit this in an exam. I say to myself, it's a mixture, but I see no squares and they're different angles. And the moment they're different angles, I want to force this to be a cos equals cos equation. So I've just written that note on the side there about what's going through my head in an exam. So if I'm going to force it to being a cos equals cos, obviously the left-hand side is absolutely right already. It's already a cos. But how can I anti-reduce the right-hand side? Well, sine of 2 theta would have come from reducing cos of 90 minus 2 theta. So I've forced it into the cos equals cos kind of way of being. Okay, so now what's my next step? Well, my next step is, well, my first option is that angle 1, which is theta minus 20 degrees, could be equal to angle 2. So I've written that in my note. The moment it's cos equals cos, or sine equals sine, actually, this first step is the same. The angles could be equal to each other. Okay, now don't forget, we always set up the second solution at the same time, because otherwise we tend to make mistakes. And what's my second solution for cos? The second solution I've written in my notes there is that angle number 1 could be equal to the negative version of angle number 2. So that's how we would do any cos equation. And now that I've set both of those up with their K360s, I can actually just solve like a normal linear equation. So if I add 2 theta to both sides, I get 3 theta. And then if I add 20 to both sides, I get 110. Now if I divide everything by 3, I get 36,67 degrees, but divide everything by 3, so plus K120. If I continue to solve option number 2, I first have to distribute my negative, so it's minus 90 plus 2 theta. And then finally, I'm going to minus the 2 theta on both sides, so I get minus theta. I'm going to add 20 on both sides, so I get minus 70. And now when I divide through by the negative, I get 70 degrees, and technically I get minus K360. And there are my 2 solutions. And so I'm just going to box my kind of little thought process along the sides, but that's my thought process for this kind of type of sine equals cos equation. Definitely, I would say the most trickiest. Right, onwards. The more we practice, the better we get. Right, so the moment I see this, it's a mixture, but immediately I see the 2 angles different. I'm like, oh, this is a sine equals sine or a cos equals cos. So first of all, I'm going to get the 2 trig ratios on opposite sides. So I'm going to kick over the cos, and it's now positive. And again, I would force this into being a cos equals cos equation. So I can leave the right-hand side. It is already a cos. However, the left-hand side, I need to rewrite as cos. And this is a little bit more tricky because it's going to be 90 minus, and it's the whole of that angle. So I've just got to be a little bit careful around my brackets there. But don't forget, if you're working off 90, your name would change to sine, so that's perfect. And now there's 2 solutions for cos. First of all, the angles could be equal to each other. So angle number 1, which is 90 minus theta plus 30, could equal to each other. So that's my first option. And then my second option, remember, set them both up first, is that angle number 1 could be equal to the negative version of angle number 2. So this could be negative, and just don't forget to put a bracket in because it's the negative of the whole angle. And the hard part is done, because now you're just solving a linear equation like you would in grade 8 really. So just multiply out your negative. I would kick this negative over to that side, so I actually get minus 2 theta. Now it's not impossible for the thetas to disappear, and the thetas, when they disappear, it means there's no solution, and that does happen, so don't let it freak you out. I've got 10 degrees on this side. I'm now adding 30, so I'm going to get 40, but then I'm minusing 90, so I actually get minus 50 degrees. So divide by negative 2, and I get 25 degrees, and technically this is minus, but K180. Great, so that's my first solution done. Second solution, multiply out my negative, so minus 30, and this is now minus theta. Oh my word, what are the chances? Now I said that only because look what's going to happen here. I've got a minus theta and a minus theta. And so what I was just talking about is happening here. So if I kick over my minus theta, so I add theta to both sides, I get no theta, so I actually get 0. And then if I do 90 minus 30, that's 60. And if I then minus 60 from both sides, I'll get minus 70 degrees. Now the reality is 0 cannot possibly equal to minus 70. And so the moment you get this, I don't really need to continue or even write this K360 because this isn't possible. 0 can't equal. So therefore there's no solution from this branch. So in this case there's actually only one solution. So therefore this is my only solution instead of having two solutions. The theta equals 25 degrees minus K 180. K as the nth of integers. That's actually our only answer. So the scenario I was just actually mentioning actually has happened here. And don't be alarmed when this happens. It actually is fairly common. Right, onwards. Last one. We've been so focusing on the fact that cos could equal cos or sine could equal sine. What about tan equals tan? Now these are actually really great because with tan equals tan, remember a tan equation, you don't have to worry about a second solution. So basically, like with cos equals cos, our first solution is the fact that 3 theta plus 45 degrees could equal theta minus 90. So that's our first solution. However, I don't actually have to find a second because as long as I write plus K 180 and not 360, that 180 automatically generates the second solution. So this is basically one line. I would minus theta on both sides, so I get 2 theta. I would then minus 45 on both sides, so I get minus 135. And so finally, I get minus, if I divide everything by 2, I get minus 67.5 degrees. And technically, this is now minus K 90. But this is a lovely equation because there's just one line, which is really nice and easy. Okay, so I know we've done a lot in the last 2 videos, and just to write a brief summary, basically all of the equations we've done in 5.4 and 5.5 have been around mixtures. And the first type of mixture is when you get a mixture, but there's a sine squared and a cos squared. So we change that, we force it into not being a mixture by using the 1 minus sine squared or 1 minus cos squared. And that either gets us, a dots or a trinomial. So we can factorize and we get 2 easy equations. So that's what we did in the previous examples, in the previous lesson really. And so finally, secondly, our second solution to these type of equations is the fact that if you realize there's no sine squared or cos squared, the next thing I check for is there a 2-term equation? Is there a sine theta and a cos theta? It doesn't have to be sine theta and cos theta. It could be sine 3 theta and cos 3 theta, as long as the angles are the same. What we do then is we divide everything by cos theta to force something to being a tan theta. Now importantly, this only works in an equation with 2 terms, because you can't have an extra term messing this up. And it only works if you're working with sine and cos of the same angle. And then our third type of option is where it is a mixture, but you've tried to look for option 1, you've tried to look for option 2, and it didn't work. And so option 3 is where it's sine and cos of different angles. And then what we do is, personally, I choose to force it into cos equals cos using the 90-degree reduction, co-ratio idea, because if I have a cos equals cos, either the angles are equal to each other, or angle number 1 is the negative version of angle number 2. And so hopefully that's a fairly effective summary of the types of mixture equations we've done so far. Obviously, sometimes not every equation fits into a box. And so it takes a lot of practice to being okay with all the ones that do fit in a box to give us the kind of courage and insight we need in order to solve those that don't fit into like a box type thing. Great, this has been a marathon. Trig equations are definitely a marathon, and well done, you have made it. But wait,